Alright, in this video we're going to implement the node class. Once again, the node is serving as our base scene item. It is, if you want to refer to it, the actor of Spacefighter. To get started, let's go down to the engine section of our project and add in a new item. And this is going to be our node class. Inside of the node class, we'll begin by cleaning up a few things, starting with the sub namespace, which we will simply remove, and we'll add in a few new using systems. I'll take out the using for system.txt, and I'll add a using for Microsoft.xna.framework, and I'm also going to add a using statement for framework.graphics. Alright, moving down to the node class itself, we need to get all of our fields established for the node, beginning with the static list of nodes to act as the flat container item so that we can go through nodes in a linear manner whenever we wish to update or draw them. So this is going to be a public static list. It will be of type node. We'll call it nodes and initialize it here. So we'll say nodes is equal to a new list of type node. Alright, the next two properties are going to give the state information necessary to maintain parenting. We're going to have a field holding a reference to a parent node, and a list of nodes to contain all of the children that this node may contain. I'm going to make both of these fields private, and we'll give access to the parent via a property. You could do the same with children if you wish to. The reason I'm putting protections over these is in order to establish a hierarchical setup, we're going to use a method that will properly set up not only the node you're looking at, but the other node, the parent node itself. So we don't want people to go in and just modify parent whenever, because that could break or cause orphan branches within the graph. So this is going to be a private field of type node. We'll call this parent. And right below that, we'll put in another private field. It will be a list of nodes, so list of type node, which we will call children. And I'll initialize that list so that we have a usable but empty list to work with. So this will be a new list of node. And finally, I'll give a property that will expose parent in a read-only fashion. So I'll make a public node property called parent. Alright, moving on from here, we need some fields to describe, or actually, hang on, let me finish off.
Just a little bit more.
It's now just a separate field, yeah. We need to finish off the get accessor for this property. So get accessor that returns the field. And spelling is fun. Return this dot parent should give us what we're looking for. Bracket to end off the get accessor and curly brace to end off the property. Alright, now we need some fields that will allow us to hold the position, direction, and speed of this node. We're going to establish these concepts here in the base node class, since node is going to be responsible for handling things like movement, and also movement is going to be tied to the hierarchical nature of nodes. So we'll begin with position. I'll make a private vector2 to hold the position data, and I'll make a public property to access the position data. We'll have a get accessor that simply returns the position. So return this dot position. And a set accessor, which I will leave blank for the moment. We'll get back to this after we have the move functionality in place. As a matter of fact, the whole reason that I'm even making position a property is the parented movement behavior of the node graph is going to be dependent on the way moving itself works. That means you could technically break the scenario by allowing absolute positioning for a parent node. You would actually be able to move a parent without the children going along with it. by hiding this behind a property, we're given the chance to go in and properly move all the children along with the parent should the parent's position ever be changed to an absolute value. So that's going to require a call to the yet-to-be-written move method, which we'll get to shortly. After position, we need direction and speed, and I'm going to make these both directly accessible as public fields. So I'll have public vector2 for direction, and a public float for speed. And I'm making both of these directly accessible as public fields because changing them has no ill side effects. You're allowed to at any moment change them. If you were to make properties, the property would be purely an accessor. There would be no additional code or checks. Moving on from here, we need to have a sprite associated with this node so we know how to draw it on the screen. We'll leave all the graphical and animation elements up to sprite itself. The sprite is just merely acts as the tie between the two, and will later be passed through using a draw method in Node. So I'll make a public sprite field, which we will simply call sprite. Now we need two more fields, and this gets into the way Node is going to work with removal. Because you can run into scenarios where two nodes might crash into each other and both nodes could explode and get removed out of the list, that would create problems even if you were using a reverse loop to transverse the list. So what we're going to do is we're going to set it up so that an update call can never actually remove nodes from the list. We're instead going to save a field which allows us to mark a node as dead without immediately removing it from the list. That way two or more nodes can be killed in the same update without causing any list problems. We'll have a utility method that can go in after the update call is finished and simply remove dead nodes one by one out of the list. That way we don't run into any problems where two things have to disappear simultaneously. So this is going to be expressed using a private field and public property. Once again, because the remove functionality is actually going to work in a recursive manner as well, meaning if you delete a high-level node, all of its children get deleted with it, and therefore setting the dead individually could cause odd problems where you punch holes in the graph by having individual nodes get removed when entire branches are supposed to get removed. So this will be a private boolean called dead, and we'll have a public boolean property called dead, which acts as a read-only get accessor. So we'll simply return this dot dead. And I think with that wraps up all the fields that we need for the node class. Now we can turn our attention to the constructor and all of the methods. I'm going to drop the constructor in place as it's relatively simple. But for the rest of the methods, I'm going to skeleton them before actually implementing them. So we'll simply do this in two passes. Reason being is that some of the methods depend on other methods. So we'll skeleton all of them, then we can put the meat in for the implementation. But to begin with, we have the constructor, which is going to be a public constructor. So public node, and we're going to require that nodes take in a sprite sheet upon creation. The reason for this is that way we're guaranteed to always have a sprite sheet to feed into the sprite, so that we can always initialize the sprite immediately upon creating the node. So node will take in one sprite sheet. We'll simply call the field sprite sheet as well. And the first thing that we'll do inside of the constructor is make sure that this node gets added into the nodes list. So we'll take nodes, and actually I don't have to access that through there, just use nodes.add, adding in this instance of node. And we'll also initialize the sprite field. So this .sprite will be a new instance of sprite, and that new instance of sprite is going to require a sprite sheet, and we'll feed that in from the parameter passed into the node's own constructor. And that takes care of the constructor for node. Now we have a series of methods that we need to put in place. We'll begin with the setParent method. This will be a public void method, and it is going to take in a node, which we'll call parent. The function of this method, of course, is going to be to take the current node and parent it to some other node. We are going to set it up such that null will be allowed to be passed to it, so that way you would do a set parent to null if you wish to unparent a node out of some hierarchy. Moving on from here, we have the move method. This will be a public virtual, or actually, excuse me, just void, not virtual. Public void move, and it is going to take in a vector2 called amount. Just so you could look at this as a relative move in nature, because we're going to move by an amount taking into account the current position. Moving on from here, we're going to have a static method that is going to handle a loop that updates all of the nodes. This loop would normally exist within the game's update method, but I chose to put this as almost like a utility helper method inside of Node because it makes the calls found within the game more simplistic. You can identify what's happening line by line instead of having a large loop in between other smaller utility calls. So this is going to be a public static method. It will be void in return type, and it will be called update nodes. And update nodes is going to take in a game time, which is just something that it's going to pass on to all the individual update calls. After this, we've got, let's see what's next. We need, I'm thinking update and draw. So both update and draw are going to be virtual. So we'll override these as necessary when we get into later classes. So beginning with update, this is going to be public virtual void update, and it is going to take in a game time, and after this method we've got draw, which will also be virtual void draw. Draw will take in a sprite batch. Alright, moving on from here, we've got the remove method. Remove is the method that will be called to indicate that we wish to delete this item out of the list, but of course the actual deletion is deferred until later, once again ensuring that we never have a scenario where we try to remove multiple things from the list in one update call. So instead actually let me get this drop down. This will be public void, virtual void remove. It is going to be virtual so that in later times we have the ability to tell when we as a node are about to be removed, because some later nodes that maintain things like weapons or other forms of state might need to shut other things down before they themselves are killed. An example of this is if the player ship happens to get destroyed while it's firing its main weapon, we want to make sure that that weapon firing is stopped as the ship goes away. Otherwise we'd have an orphaned weapon floating in the scene that continuously fires. After remove, we're going to put in the static utility method that will go through and look for all dead nodes in the nodes list and remove them. So this will be the public static void remove dead. And let's see, one more method, and I think that rounds out all the method skeleton we'll need. This final method is going to be the perform method. It will be a public void method, and it's going to take in two things, an event handler and event args. So event handler, we'll call this action, and event args, we'll take that in as E. And the perform method is designed to allow a set of functionality in the form of a delegate to be applied to each actor in a branch of the graph hierarchically, meaning that, let's say, an action represented a projectile spawning. Let's call that an action. With this perform method, we would not only use that to cause the ship to fire a projectile, since it will be recursive in nature, that projectile would also be fired from any of its children. This allows us to have sidearm-based firing capability with the ship without having to go and write weapon systems for the individual sidearms, or even any form of weapon handling on the sidearms. We can just assume that since this was part of a ship, let's take this functionality and apply it recursively to any children of a certain branch in the graph. Alright, now that all these methods have been skeletoned, let's go back up to the top to setParent and begin implementing them. So up here in setParent, we need to do 3 things in setParent. 1, we need to first check and see if we currently have a parent, because if we do, we need to get removed from that parent's children list. We need to remember what our new parent is going to be, and then set our new parent's children to include us. So basically, update the field, and then remove ourselves from the old parent, add ourselves to the new parent. Now this will also require a few checks, because 1, we have to make sure that we had a parent to begin with, and that we're being parented to an actual node, and that node is not null. So we'll begin with the check to see if, as of the time of this call, if we are currently parented to some other node. So if this dot parent is not equal to null, then we are in fact parented to something else. So let's take whatever that something else is. So this dot parent, and let's tell ourselves to be removed from that parent's children list. So this dot parent dot children dot remove, and we'll pass in this as ourselves to be removed from that list. The next thing we'll do is we'll remember what this new parent is going to be. So this dot parent will be equal to the given parent. And then one last check we'll do is we'll see if that new parent is not null, and if it's not, then we'll add ourselves to its children list. So we'll say if parent is not equal to null, then parent dot children dot add this. And I'll point out here that the reason we can set parent to null if we wish is, let's say we ran into a scenario where we did pass in null as the parent. First, if our old parent existed, we always remove ourselves from it, whether we're being set to a new parent or not. We remember that, so we can remember a parent as null if need be. And then only if that parent is not null do we add it. So this is the check that allows us to parent to null, because that way, if we are parenting to null, or basically unparenting ourselves, this never gets called, so we never have any errors by trying to add ourselves to the children of nothing. Alright, moving on from here, we have the move method. The action in move is very simple. We simply increment our position by the given amount, which would be this dot position plus equals amount. Now, since move needs to work recursively, such that if you were to move a parent object, all of the child objects should move with it. To accomplish that, we'll loop through all of our children, and we'll call move for each child. So I'm going to set up a for each loop. I'll loop through for each node called node in this dot children. So for each child in our children list, we'll tell that child node to move by the given amount. And since there's only one statement in the loop, I'm going to delete the brackets out just to save on lines in the file. So once again, we actually call this recursively. The nice thing about this is it will transverse to any number of levels deep, since we're actually making the call and not just incrementing the position. Moving on from here, we've got the update nodes method. And its job is to simply walk through the nodes list and call each node's update method. So we'll make a for loop, and we'll actually make this a reversed for loop. And we'll loop starting at the last node. So we'll grab nodes.count -1, and then we'll take each node and update it. So that would be nodes sub I dot update. Update takes into game time, which we can feed in from our past game time parameter. This is the only line in the call, so I'll remove the brackets once again to save some lines. Also note that this is a reverse loop because it's possible that a call to update could cause more nodes to be spawned if a node crashes and splits into multiple, or if projectiles need to get spawned for some reason. we're walking backwards through the list so that anything that gets spawned will get added to the end of the list, which we have already passed as we're going to the beginning. That way, any added nodes do not interfere with our position in the list. Alright, now we can move on to the update method. And the update method is used to cause continual movement based on our direction and speed, and to make sure that our sprites get updated. So we'll begin with the moving. So we'll call this .move. For the amount needed to move is going to be represented by our direction times our speed. So we'll give in this .direction times this .speed. And since we're going to treat direction as a unit vector, that way we have purely directional information and can adjust our speed independent of direction. The next thing we need to do is make sure that our sprite gets updated. So we'll call an update to sprite and simply pass in the given game time. Alright, now we can move down to draw, and draw is going to be a simple call to tell the sprite itself to draw. So we'll say this .sprite.draw, and we'll give in the provided sprite batch. If we look at the full signature to draw, we see we also need to feed in a position to draw the sprite at, and that position will be our position as a node. So we'll feed in this .position. Alright, now we can move down to remove. And inside of remove, the remove method only marks the node as dead, though it does operate in a recursive fashion, such that if you remove a parent node, all children nodes will also get marked as dead. So we begin by simply saying this.dead is equal to true, and then running a for each loop through all children, just like we had done earlier in move. So we have for each node in nodes, or excuse me, in this.children. So for each child node, we will call the remove method. So node.remove, and we'll reduce this down to one single line. Alright, next method is remove dead, and this method is going to need to loop backwards starting at the end of the nodes list all the way to the beginning and perform the actual removal where we take the nodes out of, or where we take any dead nodes out of the list. So we'll make a for loop that runs in reverse. We'll begin at the end of the nodes list, so that's marked at nodes.count -1. For every node that we find, we're going to see if that node is dead, so we'll do a check and see if nodes sub I dot dead, and if the node is in fact dead, then we'll do the following. We'll check to see if it is parented, and first unparent it before we actually remove it. This preserves any hierarchical structure. So we'll say that if nodes sub I dot parent is not equal to null, then we will take that node, nodes sub I, and set its parent to null. And we'll rely on setParent handling, removing us from that parent's children list. Once we've taken care of parenting and unparented ourselves from the graph, we can then take the nodes list and remove ourselves from it. So since we're looping through nodes using an index, I'll actually use remove at, and we'll give the index of I. And that should wrap up the remove dead method. Now moving into perform. With perform, all we're going to do is invoke the event handler that has been passed into us, providing or giving the provided event args, and then we will perform a loop through all children to run the same action as well. So we'll take our action and invoke it with ourselves as the sender and the given event args as E. And this is where the really interesting key part of this happens, is the fact that that action is always given the current instance of node. So that way, action is almost written and viewed in a flat sense, but it's known that anything that was parented into the parent originally called is going to be coming back one at a time through the sender, or through the this parameter. Now we need to loop through all children of the current node, but we're actually going to loop through in a reverse manner because there's no guarantee that the action specified isn't going to spawn or change the parenting hierarchy. It has access to the setParent method, so we need to account for that the child list may change as the action continues. So we'll need to loop backwards to make sure that nothing breaks because of this. So I'll make a reverse for loop where we loop through this dot children and beginning at children.count -1, and for each node found as this dot children sub I, we'll tell that child to perform the given functionality. So we'll perform the given action and the given event args. And that wraps up that call. Once again, I'll take the brackets out because it's only a single line to be called. And that takes care of all of our methods. Now that we have all the methods in place, and more specifically, now that we have the move method in place, I can go back up to the position property and address the set accessor for position. What set is going to need to do, since position allows you to specify an absolute location for the node and have it immediately jump to that location, that would mess up our our recursive moving system. So instead of allowing a jump to a given position, we'll take our own position into account, figure out how much would have to be moved to reach the new absolute position, and then move or apply that relatively using the move method. So we need to find the difference between the given target and our current position, and we can do that by getting the given value, so the value being the incoming new position minus our current position. That will give the amount that would need to be added to our current position to arrive at the value. So knowing this value is the relative amount we need to move by, we can say this dot move value minus position, and let's see, wrap that up, terminator, and that takes care of the set property. So again, an interesting use of value because it doesn't look like position is directly affected, but move will later affect it. So we're telling us to move instead of directly storing the position value. Alright, I think that takes care of all of the methods and properties for Node. The last system we need to account for is the collision system. We're going to implement collisions inside of Node, much like we had implemented collisions in the animated sprite collision project, where we used the example actor class to work with the sprite and the sprite's texture in order to allow per pixel collision detection. So we're actually going to grab that functionality directly from that original actor class because the code isn't going to change at all. We're going to change the terminology of one thing only because the old collision code required the actor type, and we've defined that here as node. So I'm going to go back to our working folder and go back to this original actor class. As we said before, this came from the animated sprite collision project. I'm going to grab this and drop it into Visual Studio so that I can copy some of the code out of it. The code that I'm going to grab is the entire collision region. We can expand that and see that that is in fact all of the code we had. I'm actually going to collapse it so I can select just that region, and then we'll jump over to our current project and go down to the end after our last method and paste the entire region in. Now the collision code requires two fields that we haven't yet moved over. We need an alpha threshold, and we also need the graphics device used here to reset textures element 0. So I'm going to copy those also from the original actor class. Those were up here in alpha threshold and graphics device. As a matter of fact, just for the sake of speed, I'll copy the entire block, just knowing that I need to remove the middle two. So I'll go up and I'll actually place these inside of the collision region, just since these properties are for collision purposes only. So now, let's see, if we build, actually, yeah, I'm going to build at this point to, one, make sure that we have no errors previously, and also there's going to be a few types that need to be changed where we're using things like actors. I believe we might also need a bounds property, because I think bounds was calculated, and we don't yet have a bounds property on the, let's see, on the node itself. I'm just going to copy the one directly out of the original actor.
Okay.
Now if we attempt to build, we have a few cases where we're looking for an actor which has not been defined, and that's simply because we're using nodes now instead of actors. So I'll replace both of those with node, and just to make sure the code reads correctly, I'm going to hit F2 to rename these actors A and actor B to node A and node B. So actor renames to node. And now if we build, and let's see, where was for each node and a node? And that must have just simply slipped by as a typo. Alright, with those corrected though, that takes care of all of our errors, and we have all of the collision code in place. As a matter of fact, I'm going to go and collapse that region back down. Once again, no actual changes were made inside of it. Though, before I run away from it, I do want to point out one thing. Down here inside of the collision detection code, you'll see we're taking a graphics device, or the graphics device, and setting texture sub-0 to null. The reason this line is in place is because at the time of the recording of the per pixel collision project, there was a bug in the version of XNA that we were using that required this element to be nulled out, otherwise there's a potential that get data could return an error. We're leaving this in place simply because we're leaving the code intact from the original collision detection, and it causes no problems in the current version of the XNA framework. I'm just pointing this out because if you're using a newer version of the XNA framework, the bug will probably not even exist anymore, so you can more than likely simply omit this line and the graphics device field here in the collision section. Now, since we do have it in place, I need to assign this, otherwise we're going to hit this code and graphics device being a field is simply going to be null. So we do need to remember to go into the game class and set that up. I'm going to set it from inside of initialize. We'll take our node and set the graphics device field equal to this dot graphics device. So with that set up, we should be able to build. Everything builds with no errors, and I think with that, that takes care of the node class. Again, just a quick recap, we have the necessary fields to set up a hierarchical node graph for storing, for organizing our graph. We've got position, direction, and speed fields to maintain the state of a node, though we do need to take special consideration on the setting of position to make sure that we use appropriate relative movements instead of an absolute position jump. And we have grabbed the collision detection from the original sprite collision project. So with that, I think that's all we need to cover in this video.